In the previous section, we have seen the definition of the scalar product. Now let's have a look at some application in geometry and in physics. So the scalar product of two vectors A and B is defined as the sum of the products of the corresponding components. And this can be also expressed as the product of norm of the first vector A times norm of the second vector B times cosine of the angle phi formed by these two vectors. If you have a vector A, vector B, then we say this is the angle phi. And we have seen that norm is the square root of sum of squares of the components. So this can be used to solve the following problem. Find the angle of the vectors A, 112, and B, 105. First, we compute the scalar product A dot B, which is 1 times 1 plus 1 times 0 plus 2 times 5, which gives 11. We also compute the norm of A, which is square root of sum of squares of the components 1, 1, 2, 1, 1, 2, square of that, sum of that, and square root of that. The result is square root of 6. And we find the norm of the vector B, which is the square root of sum of the squares of the components of the vector B. 1 square plus 0 square plus 5 square. The result is square root of 26. And then, if we have the result of the scalar value, which is here, and we have the two norms, then we can find cosine of the angle by dividing the scalar product by the two norms of the two vectors. So cosine of the angle is the scalar product A dot B divided by the two norms, norm of A and norm of B. And for our example, the numerical result looks like that. And then the cosine can be found as the angle phi is the arc cosine of this value. Another application of scalar product is when we want to project a vector in a given line, in a given direction. Consider the two vectors, vector A and vector B. Vector A defines a line, if it is non-zero, and we want to consider the orthogonal projection of the vector B to this line, to this direction. So it will be a vector going in the same direction as the vector A, and its length will be this side of this right triangle. So if we take the vector A and divide by its norm, we get a unit vector. That's a vector in the same direction and orientation as the original vector A, but with the unit length. And then, so this gives the direction of the result, and the length of the result is given by just the length of this side. B times cosine of phi. B times cosine of phi, where B is the norm of the vector B. If we multiply and divide by norm of A, then in the numerator we get norm of A, norm of B cosine, which is the scalar product. And here we get norm of A times norm of A, which is again scalar product of A with itself. So the projection can be written in this form. A gives the direction, this is the vector, and this is multiplied by this number. It's a ratio of two real numbers, A dot B divided by A dot A. Another application of scalar product is in physics, namely mechanical work. If you apply some force, F, along some displacement, S, then if you multiply the force in newtons times the displacement in meters, you get the mechanical work in joules. This is okay when the direction of the force is identical with the direction of the displacement of the motion. In general, you can push in different directions that you move, And then we consider two vectors. The vector F arrow, giving the force, including its direction, and the displacement S, again as a vector. And the mechanical work is the scalar product of these two vectors. From this result, we see that a scalar product may be equal to 0 if either the first vector is 0, or if the other vector is 0, or perhaps both of them. But a scalar product may be equal to 0 even for non-zero vectors if cosine is 0. Cosine is 0. Is it possible? Cosine looks like that, and it is 0 by half. So if the angle of the two vectors is by half, 90 degrees, the scalar product is 0. That means the two vectors are orthogonal, are perpendicular. And this is the case for a circular motion. If you want a point to move along a circle, then you must attract it to the center. But this force is orthogonal to the direction, so this force makes no mechanical work.